Hey everyone, we're moving into this section of our course where we're about to be exposed to a really interesting technique called cross-validation. That technique is useful for really all facets of model construction and model assessment. And so for that reason, I just wanted to build a notebook and a video to talk to you about cross-validation, what it is, how it works, and why we should care. We'll do that through a toy data set, kind of as usual. So I'm going to import NumPy for some random number generation, pandas so that we can deal with tabular data, matplotlib so that we can visualize results and the data that we're working with, train test split so that we can split data using our traditional kind of validation set approach. That's the approach that I've been discussing with you up to this point. We'll introduce, we'll actually load up a cross-validation module later, and then also import the linear regression model constructor because that's the class of model we'll be using here in this notebook. So again, like I said, we're going to look at cross-validation. We're going to look at how it helps us choose an appropriate level of model flexibility, but also how it simply helps us arrive at a stable and reliable estimate in prediction error. And we'll see how that stable estimate compares to a much less stable estimate produced by the validation set approach. So cross-validation really is a big development for us and a huge advantage, and we'll be using it moving forward. So we'll start by generating our data. The data that we're going to generate follows a fourth order association between the response variable y, and we're going to have just a single predictor x. Generating this data is not super important. If you care, here's the mathematical baseline formula that relates x, the predictor variable or the feature, and the response variable y. And then this random noise that we're adding here is what forces us into a predictive modeling task. Without this piece, x and y have a deterministic relationship between them, and there's no use for database modeling techniques. One thing to really pay attention to here is the scale of this noise. The scale is the standard deviation in the noise. So if you remember, the noise is what's going to bounce us off of this deterministic relationship. So noise will bounce us up or down on that y-axis. The average noise is 0, which is typical for linear regression. If the noise weren't averaging 0, we could just move this into an intercept over here and recenter the noise at 0. And then the scale parameter, like we said, is the standard deviation in that noise. This is unexplainable error. And so when we build a model, we're not going to be able to do better than this. This is sort of our target. When we're modeling in the wild with real data, of course, we don't know any of this at all. We don't know the true relationship between the predictors and response that we're trying to model, and we certainly don't know the extent of the noise. So we've built at this point in the first 2 lines our predictor x and our response y. We're going to collect x and y into a data frame. We're going to use train test split to split the data into training and test sets. I'm not going to split into a safe set here because we're not going to go that far. I just want to be able to build a model on the training data and assess it on the test data. Excuse me, sorry. And then we'll output the header of the training data. So we can see the x coordinate or the input feature and the response that we're trying to predict. What's more useful tabular data, though, is seeing a plot. So here's a plot of the input feature x versus the response y, and we can see sort of a complex relationship between the two variables. And this is what we'll try to model. So let's build and test several models. What I'm going to do first, though, is in order to increase flexibility, we're just going to add higher powers of x. So like x squared, x cubed, x to the fourth, and so on. So we'll need to attach those columns to this data frame, and in particular to the original data frame. And so what we'll do is we'll kind of do this efficiently. I'm going to use a loop here to attach new columns to the original data frame. Those new columns will be higher powers of X. Once we have those new columns attached to the data frame, we'll resplit our data in the same exact way as we split it before, with the same training set size and random state parameters. Once we do that, we can see that we've got a lot more columns available to us in the training data. So we have the original X and Y, then we have X2, which is X squared, X3 is X cubed, and so on all the way up to X to the 8th. Now that we have that, let's build some lists to contain uh, our training root mean squared error. So we're going to build models and compute the training error. We're just going to initialize that list with a bunch of zeros for now. We'll do the same for the test root mean squared error. And then we'll also have another list which just contains the order of the model. So this is just counting straight line model, which is order 1, quadratic model is order 2, all the way up through order 8, remembering that Python is right endpoint exclusive. So this will count from 1 through 8, stopping before it gets to 9. Those lists are now initialized, and we're ready to build and assess our models. So there's a giant code block here. We're going to create the training data. We're ripping off the response column. We don't want the model to be able to see that and use it to predict itself. And then separately, we'll store the response variable. We'll do the same thing with X so that we can make predictions on X test once our model is fit on X train. And then we can compare those predictions to the true response values in the test set. Excuse me again. We're going to use looping to efficiently fit these models. So here I'm creating an instance of the model. I'm fitting the model on the appropriate number of columns. Then I'm going to compute predictions on the training data. That will help me compute the training root mean squared error, and then also on the test data, computing, eventually helping to compute the test root mean squared error. We'll produce some plots, so overlaying the predictions on top of the training observations and the test observations, so we can see a little bit about how the model kind of looks and feels, how it's increasing flexibility by adding these extra columns changes the model fit. Then we'll compute the training and test root mean squared errors. That's the ugly formula that we've been using up to this point. And then we'll fill in those errors into the train RMSE list and test RMSE list that we initialized earlier. So lots of code, but it's going to fit models and build some pictures. And so if we scroll back up to the top here, we can see that the first model was a straight line model. It fits the training data okay, and the test data a little bit more poorly. We add some flexibility, so a second order model is allowed to have one bend in it. Here's that. We have a third order model, which is allowed to have two bends. And then as we increase the flexibility or increase the order of the model, we're allowed to have more bends. That's going to increase the ability of the model to fit the training data. Remember that fitting the training data is what the computer's objective is, but our objective is really to build a model that's going to fit unseen data or really future data pretty well. And so the test data is playing that role. And so we can see once we increase flexibility beyond fourth or fifth order, the model's not changing a whole lot. Okay, so now what may be more interesting than just seeing the model's predictions overlaid on top of the training and test data is to see how the error metrics change over time or with flexibility. So that's what this plot is going to do. I'm going to create a line plot. The horizontal axis is going to be the order of the model. So as I move to the right, we'll be increasing flexibility. And then the vertical axis is going to be root mean squared error. So this first line is creating the training root mean squared error, sort of a profile of that as model flexibility increases. The second line is just putting points on top of that line so that we can see that we really do have discrete points. The third and fourth line are doing the same thing, just for the test errors instead of for the training errors. Then we're adding some titles and axis labels. And so here we can see that as model flexibility increases, the training and test error both decrease. They both decrease until we get to about 4 or 5, and then the test error starts to increase again. The training error continues to decrease a little bit. So in general, adding flexibility to a model, we should expect training error to decrease and test error eventually to start increasing as our model becomes overfit to the training data. And so what we can, these plots, I should say, are called elbow plots. They're really pretty common. What we're looking for is the point at which the elbow starts to bend. Dropping the test error as far as possible before it starts to rise, indicating overfit. So to the left of that minimum, we have underfit models. To the right of the minimum, we have overfit models. And so here we see some candidate models, probably degree 4 or degree 5 is the best model to move forward with, according to this plot. One thing that we've talked about up to this point is the idea that using the traditional validation set approach is somewhat potentially unreliable. And the reason for that is that we're subject to just the random data that fell into the test set. And I'll show you kind of this in action towards the end of the notebook, but with different test sets, we'll get potentially drastically different error estimates and potentially different model choices. And so let's take a look at using an advanced technique called cross-validation. If you remember from our initial discussion on cross-validation, the way this works is we take our data set and we break it up into different folds. So typically 5 or 10 folds are used. These are just groups or subsets of the data that we have access to. Each of our folds will take one turn being left out and acting as a test data set, while a model is fit on all of the remaining folds. And so with cross-validation, we're not going to fit one model and get one error estimate. We're actually going to fit many models. We're going to fit, and we'll get many test errors. We'll get the number of test errors we'll get back is equal to the number of folds we have. Each individual fold will have one chance to be held out as the validation set. Okay, so again, let's try this again. I'm importing the functionality we need. So cross-val score is going to score a cross-validation model. And kfold is actually just going to compute the folds for us. So it's going to assign the data to the folds. Like we did earlier, I'm going to create a list to store our cross-validation errors. Then I'm going to create our data that we can work with. So instead of calling this X train or Y train, X test or Y test, I'm just going to call this X CV and Y CV. And actually, I'm going to go back to the original data to do this, just so we have more data to work with. And then once we have that, we're going to loop through again to fit and assess models efficiently. We're going to create an instance of a linear regression model. We don't need to fit it actually. We're going to compute the folds on our data set. So this is going to assign each observation randomly to one of 10 folds. The folds that we build will be approximately equal in size. Then we're going to use cross-val score to fit linear regression models on the data that we've provided. It's going to score these models according to the mean squared error. So this is not root mean squared error. It's mean squared error. And it's negative mean squared error. The reason for this is a programmatic decision. These optimization functions are typically designed to minimize a quantity, maximize a quantity. And so equivalent to minimizing the mean squared error is maximizing its opposite, maximizing the negative mean squared error. And again, this CV is defining the folds. So the cross-validation folds that we're using were defined by KF coming out of K fold. Once we have the scored model, so CV error is going to contain a bunch of error metrics. It's going to contain actually 10 of them, one for each fold, uh, coming from a fitted model. The model fitted on 9 of our folds and assessed on the remaining held out fold. We're going to use that error metric to populate our cross-validation error. What we're going to do is we're going to aggregate the 10 error metrics or error estimates that we get, and then we'll call this cross-validation error. We're going to multiply the cross-validation error by -1 to get away from this being the negative mean squared error and make it positive again. And we don't want mean squared error, we want root mean squared error. So that's what that star 0.5 is doing. It's taking the square root, remembering that an exponent of 1/2 is the same as taking the square root of a value. And then once we have those root mean squared errors on each fold, we're going to average them together. So we'll get the mean. We'll call that the cross-validation error. Once we have these, so we're going to have a cross-validation error for each level of model flexibility. Then we'll plot it. So similar to what we did before, we'll build a line plot where model flexibility is along the horizontal axis, and then the root mean squared errors on the vertical axis. This is in the cross-val errors list. We'll add a scatter plot just to put dots on top of those lines and include some axis labels and title for context. Then we'll show the plot and we'll print out the cross-validation errors. And so what's nice here is we see underfit models when the model flexibility is at first, second, and third order. We see a big drop when we get to fourth order, some stability between fourth and fifth order, but then as we get to sixth, seventh, and eighth order, the error begins to rise again, indicating that we've overfit at that point. So again, we notice from cross-validation that the appropriate level of flexibility for our model is a fourth order model or a fifth order model. We don't get much benefit here from going from fourth order to fifth order. So what we'll typically do is choose the model with the lowest level of flexibility that achieves the desired error metric that we're working towards. So here, since there's not much difference between a fourth order and a fifth order model, we would choose the fourth order model. There's an increased risk of overfitting when we move to a fifth order model, and we'd like to avoid that. Essentially, the risk is not worth the reward. And we can see the individual cross-validation errors here. So this is with a first order model, a straight line model. This is with a model that's quadratic, has a single bump. Here's our third order model. So it has a cross-validation error of 219. If we continue to run this, so the paragraph below here says the cross-validation error is remarkably consistent. I'm just going to drop the size down here for a second. We'll run this over and over again. We're going to pay attention here to this value, the 219.4. That's the cross-validation error estimate for the fourth order model. If we run this again, we get 208, 218, 215. So that cross-validation error estimate is bouncing around, but not very much. 213 now. Let's take a look at, so before we move forward, what has cross-validation done for us? Every time we run this, we see that cross-validation estimates that we get a big benefit by using a fourth order model. So we see the bend in that elbow plot is at a level of flexibility of 4. This is identifying that we should be using a linear term, a quadratic term, a cubic term, and then a fourth degree term for x in predicting y. And it's also telling us that the root mean squared error that we should expect to achieve is somewhere around 200. So all of these values have been somewhere around, this is, I think, the lowest we got, 197. The highest we got was about 220. So somewhere in there would be our expected root mean squared error. And if we remember back to the beginning of this notebook, when we computed, when we built the data set, I should say, the standard deviation in that noise that we added was 250. So we're pretty close to that, actually. We're around 200 to 220. What happens if we don't use cross-validation and we just use the validation set approach that we had earlier in our class? So the original approach that we were exposed to. What I'll do is another code block. We're just going to split the data. I'm not going to use a random state here. So every time we run this cell, we'll get something different. Once the data is split, we'll build X-train, Y-train, X-test, and Y-test, again, so that we can build and assess the model. We're going to fit our linear regression model, and let's fit the one that we know is the right one. So the one that includes up to the 4th degree term. And then let's compute the test error for that model, and we'll print it out. And let's do this a handful of times. So here I get a test RMSE of 154, 305. So you can see already that these are bouncing around all over the place. And so sometimes we get an easy test set, sometimes we get a difficult test set, like this one was quite difficult. The problem is we have no control over whether we get an easy or hard test set, and we don't know whether we got an easy or hard one. And so having validation error estimates that bounce around like this is not helpful because it doesn't help us determine how accurate we should expect our predictions to be. Cross-validation error, on the other hand, so if we run this over and over again, we consistently get numbers right around 210, which is a little bit low given our original standard deviation, so the standard deviation of the noise, but remember that we're restricted to the data that was generated at that point. So the data generated at that point may have actually a lower standard deviation than what we requested. But again, cross-validation, much more stable error estimates. All of these are right around 200 to 220 or so. But the validation set approach has much more wildly varying root mean squared error estimates. Remember, part of the reason we're computing these error estimates is, yes, to assess model fit, but also to build some expectation for how well we expect our model to perform. With cross-validation, we get a much more reliable, trustworthy estimate. With the traditional validation set approach, we may get an estimate that's much too low or much too high. And unfortunately, we don't know whether our estimate is too low, too high, or about right. The other advantage that cross-validation gave us was with selecting the appropriate level of model flexibility. So again, every time we ran this code cell, we got an elbow plot. Each time we ran that elbow plot, we ended up with somewhere around a 4th degree or 5th degree model. And it was clear that 1st, 2nd, and 3rd order models were really underfitting. And so that's some of the advantage to cross-validation. There's more to this story. There's even greater benefit that cross-validation gives us, and we'll talk about that later in our course. But for now, hopefully this has been a useful introduction to the benefits of cross-validation. Thanks, everyone. I'll see you next time.